Hey folks. Okay, well, continuing with the code generation side of life, we were looking at selection and iteration next. So again, the general idea is we've got our code broken into blocks of sequential statements where there's kind of no labels in between, in the midst of these blocks. There's a unique entry point at the start, a unique exit point at the end, and there's no other branching that takes place, right? That block begins with a label, ends with a branch, and that's pretty much it. So if this is the idea, then we've got kind of some kind of control structure that's modeling how we get the flow between the blocks. So typical idea is a control flow graph where you've got nodes for the blocks and then just directed edges for where control can transfer from the end of one block to the beginning of another. So we've got this kind of general model in the back of our mind as we discussed earlier. So within that idea, we've got this chunk within a block where we've got a bunch of instructions in the block. Now, in the source code, of course, we have to write the code in some kind of order. So when we've written the source code, we've written the instructions in a specific order, but often it doesn't have to be that precise order that the instructions are run in. So if we look at the example here where we assign 1 to x, 2 to y, assign z the sum of x plus 1, assign y the sum of y and z, and then increment x. So we've got this sequence of 5 instructions, and the programmer wrote them in this order. But it doesn't really matter what order we do the first two statements in, right? We can assign x and y in either order. For the assignment to z, step 3 here, we can do it before or after assigning 2 to y, right? It's independent of y. When we get to that y instruction where we're adding y to itself, or adding y and z and assigning the result, there it pretty much has to come after instruction 3 because it needed the updated value of z, and it has to come after 2 because we needed the updated value for y. So we start building up this sort of dependency graph of what order the instructions have to be in, which instructions depend on which previous instructions. Right, that final increment of x has to take place after we use the old x for assignment or for step 3. So you wind up building this kind of a graph saying, okay, well, 1 has to happen before 3, and 3 has to happen before 5. 2 has to happen before 4, and 3 has to happen before 4. So you build up this graph. And as long as the instructions get generated in an order that obeys the rules of this graph, we're okay. So in this particular case, there's about 7 or 8 different possible orderings that we could come up with for those 5 instructions that would all be valid, that would all still result in the correct final result, a valid sequencing. So later on, we'll come back and, as part of our optimization ideas, we'll look at this notion of instruction scheduling. What's the best order to pick these things in? And it's going to depend on a huge number of things. Some of these instructions are going to be slower than others. Well, maybe not these particular instructions, but some instructions are slower than others. Some use more resources than others. Maybe we've got multiple processors and we can do some instructions on one and some instructions on another. So there's all sorts of considerations that will come into how and when we carry out the specific instructions. But we'll come back and address that another day. For now, let's just assume that we're going to come up with some kind of a decent ordering of the instructions within a block. So what we're really interested in is the transfer of control between blocks. And for the moment, we'll look at selection statements, so ifs and elses and switches and that kind of thing. So most of the basic if-else idea we covered back in our section on Boolean operators, just because our Boolean operations were so closely tied to this basic idea of branching. So for the most part, we covered the ideas there. A couple of points that we didn't get into. So a general idea, we've got some kind of a condition. If it's true, we'll do one block. Otherwise, we'll do another block. Is the most general idea. And then after either of them, we'll go on to whatever the rest of the program happens to be. There's a few things that we didn't get into when we were looking at this. It might be possible for us to, in some way, prioritize one block over the other. So it might be possible to make it easier to jump to one particular block or to execute that particular block more efficiently. And the reasons we might do that are if we know that this condition is almost always true or almost always false, if there's only one time out of 1,000 or one time out of n or whatever it happens to be that we're going to hit block A, or one time out of n that we're going to hit block B, then we might have a good reason for prioritizing the block that's used most often. Similarly, if one of the blocks is way slower or way longer than the other, we might have a reason for prioritizing one block over another, right? For trying to put our optimization efforts into the places where it's going to do the most good. It might be the case that one of these things has a bunch of nested ifs in it that's going to make it more difficult to optimize or make it, again, slower to run. So there's all sorts of different conditions that might cause us to actually carry out some specialized optimization to focus on one block rather than the other. And again, stuff for us to come back to when we get to our optimization section. Optimization section's growing and growing and growing, as you can tell. So what we didn't get into was the idea of switch statements much. So the switch statement or a case statement or whatever your language happens to call it, where we've got a whole bunch of different cases for a particular, we look at the value of an expression and say, does it match this case, does it match this case, does it match this case? And maybe the first case that it matches, we do the block of code for that case and then jump to whatever's after the switch statement. So this is our pretty general idea for how we're going to tackle this. So the most basic idea is just to think of this as a whole bunch of cascading if-then-elses, right? If A is equal to, or if X is equal to A, then we'll do block B, else. If X is equal to B, then we'll do block B, else. If X is equal to C, then we'll do block C, and et cetera, et cetera, et cetera, and then some final default case down at the end. So in that case, we could just take whatever kind of assembly language process, whatever code generation process we used for an if-else, and just do it a whole bunch of times to generate all of these cases. So that's straightforward, but it might not be the most optimal way to produce our code. We might be able to produce much more efficient code or much more compact code to do the same thing or to accomplish the same results. So suppose we've got a really big set of cases, right? It's not going to matter much if we've only got a few cases in our switch, but if we've got a switch statement with a lot of cases in it, then maybe rather than doing this kind of linear search through our if-then-else conditions, maybe we set up something a little different. So maybe we set up essentially a table where each entry in the table has the value and then which label to branch to. So it's got a value and an address, essentially saying, okay, if it's this value, we want to jump to this address. So in that case, what we can do is generate the code to do a binary search on the values in that table and find the right one. And if it's not in there, we do the default. Right? So you stick the orders in stick the values in the table in sorted order. This assumes that there's some kind of ordering that we can use. So we stick the values in the table in sorted order, and then we do a binary search on it. And yeah, we're getting order log n execution time instead of order n time. Now, the trade-off is that we're, of course, generating more complex code. We're actually generating code to do a binary search, which might mean that the compiler is, generating its own binary search routine that works on these things. But again, we've got some kind of code that we're generating to perform this binary search, and we're having to do at compile time the sort on our data values to stick them in the table in the first place. So there are some options for how we can go through and do some optimization. Let's take it one step further and say that we've actually got a bunch of sequential values that we can work with, or nearly sequential, a bunch of, if they don't have to be listed in sequence in the switch statement itself, in the source code, but as long as the set of values covers some sequence, or maybe with a gap or two that we send to the default case. So let's say we've got cases 3, 4, 5, 6, up to 17, or A, B, C, some nice sequential ordering where the underlying values are essentially integer based, right? Maybe some kind of character code for the characters here. But we've got this this idea that we've got some integer sequence of cases that we can rely on. Then what we can do is think of these like indices into an array. So we'll create an array of labels, right? An array of addresses, saying, okay, if it's in position 3, we jump to the address for 3. So we're going to look at the value of the expression that we're switching on. And if it's a case like this where our first value starts at 3 or something like that, then 3 is obviously going to be in position 0 in the array. So we treat it like array indexing, where we subtract the base index and say, okay, from there I can compute the offset to the right spot in this array, in this table, to find the label I should jump to for the code for that particular case. So you're just treating this like an array with a sequence of indices, and we're figuring out the right offset to get to the right spot in the array to get the address of the label that we should jump to. So again, this way we get a nice fast, constant time operation to actually jump to the correct spot and then jump to the correct block. So again, an interesting possibility. And again, there might be gaps in here, so maybe the switch statement had values for 3, 4, 6, 7, 8, 11 or something like that. Then for the ones that are missing, we just say, oh, those jump to whatever the default case is. So you can go through and clean this up even if it's not perfectly suited in the source code. So again, different ideas we can tackle to try and optimize the approaches that we're using. So the next part I wanted to get into was the iteration side of things, so loops. And again, the details, just like with our ifs and elses and whatnot, are going to depend fairly heavily on what kind of test and branch operations are supported in the assembly language that we're using. So that is going to have a significant impact. And one of the things that you'll notice as we go through some of our examples here is that we're not necessarily going to generate the most optimal assembly language constructs when we put together our loops in the first place. So we're going to come up with a framework for loops, for while loops, for repeat until loops. And then what we'll say is, okay, this is the framework, this is what we'll generate, and we'll look at a framework that, again, is suitable for later optimizations. And the way it'll tend to show up is when you're looking at this, you'll see one entry test for whether you get into the loop the first time or not, and then one repeat test for whether or not you should go through and do the iteration for the loop another time. And you'll see that the code for these tend to look pretty similar, and you can right away jump to the idea that, we can get rid of one of those tests if we just restructure a little bit. For the moment, we're going to leave this more generic structure in the hopes that we can use it to improve our optimizations later on, trying to use information from the body with the repeat test, or information from the setup with that initial test, independent of one another. Alrighty, so I wanted to dive in and look at, again, just a few different basic loops and common constructs for them. So let's say we've got a for loop where we're saying, okay, I'm going to start with a value of m, and I'm going to go up to value n, and each time I go through the loop, I'm going to increment by I. So we'll keep this kind of fairly generic, and each time through the loop, I want to do this block of code A. So yeah, it's pretty straightforward. We want to load the value of m into whatever register we're going to use for our counter, right? The register that's holding our sort of x value. We want to load the value for our stopping case into another register, so we'll call that register n. We'll have to load the value we're incrementing by, into another register. So we've got these three registers for the x value, the n value, and the I value. And then we just want to go through. Let's see if we get in the loop the first time, because of course m might be bigger than n. So we'll compare x's current value to n, and store the result here in a condition register, or in a register. And so we're storing a true-false result is x greater than n or not. And then we'll have a branch instruction that just says, okay, based on that true-false result, we'll either jump to the exit or we'll jump to the entry and do the block of code. So we'll have our block of code, right, whatever block A does, and then we'll have the test to see whether or not we should go back and do it again, right? So we've got to add our I value to X, right? So we're adding our register I content to our register X content and updating register X. And then again, doing our compare, right? Compare X to N and see if now we should continue. And again, this is one of those places where we're going to use a separate condition register here, just in case we can optimize this chunk of code later with the block A code, as opposed to optimizing this other chunk of code with whatever preceded it. So we'll come back and take a look at that. But again, you see the structure is very effective, right? Very simple. It's not going to be difficult to generate this stuff. And again, hopefully some of these things are already in registers previously. So while loops, same basic idea, right? If we're saying while and some condition, so here we'll use our condition as while m's less than n, we'll do some block of code. Again, for a while loop, we're assuming that it's up to the programmer who wrote the source code to do whatever changes are necessary to m and n, so they don't wind up with an infinite loop, but that's their problem. So we load the values of m and n into registers. We do our comparison to see if we should get into the loop in the first place or whether we should jump to the exit. Right? We do the block of code, and then again, we compare the current value of m with the current value of n, and again, decide whether or not we should branch to do the loop again or whether we should exit. So I don't think there's anything too shocking there. Repeat until, same sort of idea, just the test is at the end. Right? We load our two values, we run our block of code, and then we test to see whether or not we should go back and do the block of code again, or whether we should drop out and go with whatever's next in the program. The only other thing I wanted to mention with the loops were some of the special features that languages often throw in. I should have thrown in a final or last or something like that as well here. But with things like break or continue or go to, for the most part, these can just be a single, unconditional jump. If it says break, then we go straight to exit, right? We jump to the exit. If it says continue, we jump back up to the top of the loop, whatever the entry point was. If it's a specific go to statement, then we do what it says and we jump to wherever it specifies. If there's some kind of a final or a last, some kind of instruction that says, at the very end of the loop, no matter what, do this, then we just have our exit actually is or we have a preliminary exit, if you like, this last label, where instead of jumping to exit when we're doing our loop tests, we jump to this last, and then at the end of the last, we jump to the exit. So all of these things can be implemented fairly easily. Right? There are no huge complications in trying to automate the generation of this code. All of the fun comes in the optimizations later on. All right, I think that was everything I wanted to hit on iteration and selection. And next time around, we'll get into looking at function calls.